welcome to this new colloquium in the series of ICMM's Colloquia. So for those of you who don't know me, I guess everybody knows me, but just in case, I'm Eduardo Hernandez. I work here, as you might know. And it is my pleasure today to introduce another man of the house, Cefe López. Cefe is the leader of the photonic crystals group, a group devoted to the fundamental aspects of light-matter interaction, but also its application in specific devices that they design, synthesize, and characterize. Now, it was only yesterday that we had, in this very room, another seminar cautioning us against the use and abuse of scientific metrics. So I'm not going to mention any numbers regarding Cefe's scientific output, just to say that by any standards that you chose to use, his scientific career can only be described as a very productive and highly successful one. Today he's here to tell us about another more recent interest of his, which is artificial intelligence, an interest that he shares with many of us, I'm sure. And in particular, he's going to tell us about things that artificial intelligence and material science can do for each other. So we're all waiting to learn from what you have to say on this topic to us. Thank you very much.
Thank you, Eduardo. It's a pleasure for me to be here today, and a greater pleasure to have been introduced with such praising words, which I don't deserve. As Eduardo was saying, I have been in this house for many, many years, and I have centered my interest in the light-matter interactions, as he said, but from a perspective of order and disorder, mostly my group, as he said, is photonic crystals, which are defined as order structures for photons, but disorder is also very, very interesting. And recently, we've drifted into some statistical physics interests, which inevitably has led us into artificial intelligence. And it was very lucky that this discipline doesn't require order and can be both achieved with order and disorder structures. And this is something that we will see along the talk. I'm very opinionated sometimes, and my original title was Things That Material Science Can Do, and so on. And that could be taken as I'm going to talk about all the things that can be done, but I've added a word to the title, which is Some Things That Can Be Done, because initially I prepared a presentation that comprised 90-something slides, and I believe in an hour it's virtually impossible to run through them. So I shortened that to 60 or so, and there's a bar, a progress bar up there, so if anyone reaches to here and is too sleepy, he can know that still there's a lot of time left, so he can leave, and nobody will be offended. So this title means that material science can be a tool or can be a customer to artificial intelligence. So I divided my presentation because my audience, I know, is so varied, and we are all so special. There are many concepts, many subjects, and many topics that should be addressed, or presumably should be addressed. And this talk should be focused in different directions depending on a more selected or more homogeneous audience. So it was very difficult for me to choose what to talk about and what to leave outside. There are many things that can be said, but because my scientific character has always been driven by curiosity. I like understanding the fundamentals of as many things as I can. So this is why I'm going to give a sort of tutorial on an introduction, looking into some details that are important for artificial intelligence, and in particular for how hardware can be done and how artificial intelligence can in fact be deployed into solving problems for people. So these are the chapters I'm going to address. So I don't think I need to justify or to give a rationale why artificial intelligence is important, because it's on the news every day, every hour. In fact, the big industries of information are all in artificial intelligence, and last thing I heard is data from which they feed, it's running out. It's amazing, but for instance, the artificial intelligence from Microsoft is feeding from the data in Google, YouTube, and they are suing each other. So we are the product, and we have to be aware of that. Anyway, in an academic speech, you have to give an introduction and a motivation and the rationale. And the rationale is the big data is overwhelming us, so we have to deal with so much data that we need new methods. This is what machine learning is all about. However, I want to delve also into physical limitations, what can be computed and what cannot. And after that, I think I have a very good excuse to invoke artificial intelligence, because the brain is a marvelous organ that deals with lots of data in no time at no expense. So big data, as I said, unstructured information is generated every second by the terabytes. So last time I checked, it was about 80 terabytes per day. And the rate of growth is amazing. It doubles every, well, this was a year ago, every 48 months. And in 2020, only 64 zettabytes were created. The storage capacity is also running out, and only 2% of the data generated can be stored. All the rest is lost. And it doubles, even though it doubles every 40 months. But it is expensive. It's not only money expensive, it's also energy expensive. And the computing power, you know, everybody knows, the Moore's law is already exhausted, and we need some new paradigm. However, as I said earlier, computing is not for free. And for instance, the storage is limited because there's a limit to how much information can be stored per unit volume and unit energy. And this is given by the Bekenstein bound, which says how much entropy can you store in a sphere of radius r at the expense of the energy E. So much for the processing velocity. There's a physical limit to it, which is the Bremerman's limit, which tells you at which velocity can you switch bits, for instance. And there's a limit to that. And with the whole mass of the universe, you wouldn't be able to compute all the moves in a chess game in less than 10 to the 16 years. So obviously, this is very conceptual, but I want to highlight that nothing is for free. The transmission of information is also expensive, in the sense that if you want to transmit through a cable, you need energy, and the amount of energy per unit time depends on how much energy you spend to do it. Okay, so this is none of these are for free. And not only that, the communication lag. There's another theorem, the Margulis-Levitin theorem, that tells you that the number of changes of a state per unit time is limited to this bound, which is the energy over h. And if you translate this into computing, this means that you cannot compute faster than 6 times 10 to the 33 bits per second, operations per second and per joule. So if you want to compute faster, you need to spend more energy, okay? More fundamental limits. The energy supply is also a limiting factor, and if you realize that if you place a question and receive an answer, when you receive the answer, for instance, if you say 4 is 2 plus 2, the question is 2 plus 2, how much is that? You have more data than when you have 4, because the answer tells you what is the result of the computation, but this result can be achieved from many different ways. So this is an increasing entropy, because there are many ways to add 4. So you can have 2 plus 2 or 1 plus 3 or 0 plus 4. So this increase in entropy means dissipation, and this means you are losing energy, wasting energy. Or in each time that you have a gate with more inputs than outputs, you are losing information and you are dissipating energy. So this is a curious thing. For instance, the energy consumed by an irreversible change, if you have a reversible machine, it doesn't matter, but real machines are irreversible. So every time you change a switch, you have to spend at least kVt log 2, if the switch is binary, obviously. And as I said earlier, I wanted to say that my background is I was a peasant when I was a child. I lived in a village, in a farm, and well, the house where I was born only had telephone in the 80s, for you to imagine. There are many people here that were born afterwards, and I hadn't a phone. And my neighbors had family on the other side of the river. I was by the river Navia, so we lived in one of the banks, and their family lived on the other. I was surprised the other day at checking that the distance in straight line is only 2 kilometers, but driving or walking or going through the Chalano, through the river, took a few hours. And so they had a code to send information to each other, which was, because there was a straight line of view, this usually happened by San Isidro, because that was the fair of this village. And so if, for instance, if they wanted to tell, are you coming to the feast? If the answer is yes, you shine a sheet, a bed sheet. You place it in the lawn so that the others could see, and that was one bit of information. And as you can see here, this limit is, if you run the numbers, is about 10 to the minus 19 daily diets. So the effort of putting that information in the channel was obviously not a daily diet, but it was something that consumed a fraction of the energy spent by these people in a day. So we are far from this limit, but the economy of computing has to be taken into account, okay? This is a very important point also. There's a paper, recent paper, in which this guy, Bobson, is short for some Russian name, Bobsonovich or something like this, but he likes to be addressed as Bobson. He makes a parallel between information and energy, and he makes the case for the fact that information can only exist as embodied into matter. This is arguable, but it's interesting. I wanted to bring it here. Okay. So we are worried about energy, we are worried about economy, efficiency, and so on, and we have the inspiration of the brain the brain is a wonderful organ, as I said, and it has an immense power, and this power can be understood if you just think that, for instance, the game of Go, which is even more complex than chess, there was you have to, today is the day of the book, so I can also delve into conversation, because colloquium means together speaking, so we should have some intercourse. Today is the day of the book, and there's a book that I recommend. I was recommended by David. Maniac is by Labatut, and it's the story of, mostly the story of von Neumann. Von Neumann invented the mathematics for quantum physics, then invented the theory of games, and then invented the computers as we know them today. So this guy is amazing. And these computers have already overcome the master of the world in Go. And there's also a documentary that you can watch in YouTube on how this happened. And these guys are the brains behind Google, and they created a problem that only a few years ago were able to defeat a human in the most complex game that exists so far. But this is an achievement. It's like if you say that there's a machine that jumps more than Bubka, 7 meters or 20 meters, it's not amazing, it's no wonder. Nevertheless, this was done at the expense of a lot of energy, because the brain runs at 20 watts, more or less, like a very low power bulb. Whereas these computers, if you compare, for instance, how long a brain can work with the budget of an artificial neural network, you have to compare figures of the order of 6 years versus 80 hours. In addition to that, this program is it's very efficient, but it's only capable of playing Go, although they have trained it to play chess also and so on. But the brain is a versatile thing. It can invent, it can plan, it can plot, it can compute, it can play, it can imagine, it can dream. In the end, maybe you can ask me my opinion about whether computers can do all these things at the end, but this will be subject for conversation. So let's go into computing. Obviously, computing is solving problems, answering questions, or deciding behaviors. And there are some things that have to be taken into account because not everything is computable. And what is computable is the subject of this guy's life, short life, by the way. So computing is taking data, processing it, and giving us an output, an answer. Most problems can be put in the form of algebra or mathematics or calculus, computation, and so on. So most problems can be run with numbers and symbols and this kind of things. So if a number is computable, this was a concept by Church, this guy here, and Turing in 1936 came to a conclusion that computability, as he defined it, was very similar to effective calculability by this guy. And he imagined a machine that looks like this picture here. I put it small because its details are not interesting, because nobody is going to build a real Turing machine like this. But his idea was a machine that was fed with a tape in which there were boxes where you could write symbols and change them afterwards, a head that read what was written and write a new symbol in place. It had a set of rules, and then it had data. So the data was written on one part of the tape, and as the machine was running through the tape, it was computing. Every computing step comprise reading the tape, rewriting it according to the rules, set the head to a new state, and move along the tape. And obviously, my mind is incapable of imagining how Turing was thinking about this. But obviously, you have to write a part of the tape until it begins and give it the first instruction, read the first datum, and then according to the rules move to the left or to the right and write a new character and so on. And with this machine, those who know have decided, and there are theorems about that this machine was capable to compute any problem that was computable. However, there's this halting problem, which is the equivalent of the Gödel's theorem. Gödel's theorem says that it's impossible to build a logic system based on axioms that can decide that everything is true or false, or something like this. So this is running this argument. Alan Turing also reached the same conclusion, that there are problems that cannot be solved. There are certain things that cannot be said whether they are right or wrong, or true or false. Okay. So if you give such a problem to this Turing machine, what this translates into is that the machine never stops. There's no satisfactory answer where the machine says this is the end of the computation, because the decidability of the problem is not existent. Now, obviously, if you talk about problems and solving them, you have to establish a metric by which you measure the problems, and typically they are measured by the number of steps, or a time, or the resources consumed to find the answer to the problem. And typically they are defined as the number of steps or lines of code or things like this as a function of the size of the input. So if you place a problem with many numbers, or twice as many numbers as other, then you need twice as many number of steps to solve it, and so on. You call it polynomial if this the number of steps required are always bounded by a polynomial of the degree n of the input size. For instance, the question n, given a number, is it prime? It's polynomial in n, the number of figures of the number. Ordering n elements is n factorial size. Finding all the subsets of a set of n elements is 2 to the n kind of problem, and so on. By the way, there are no algorithms that can produce random numbers, and this is a problem, a technical problem in actual science. And when you ask your computer for a random number, it's never truly random, and unless the computer resorts to using the position of the mouse, or the temperature in the temperature of your Windows screen, or some things like this. But it's impossible to generate an algorithm that gives a truly random number, okay? Because at the end, it has to reach to go back to it can generate 1,000,000 then, but the 1,000,001 is the same as the first. So, okay, here comes artificial intelligence. So artificial intelligence is it's very difficult to define, in fact, but it's an imitation of the behavior of generally superior animals and so on. And it's divided into general and narrow artificial intelligence. In a general artificial intelligence system, the system is capable to succeed in handling situations qualitatively different from those for which it was created. Okay, so if you prepare a computer to solve, find if a number is prime, it won't be able to find the height that a ball can reach when it bounces in some circumstances. However, there's the narrow artificial intelligence, our system capable to carry out certain behaviors only in certain contexts. So our intelligence in general has many aspects that some of which have never been addressed by machines, and mostly what machines address is machine learning, because this involves only dealing with data without having much creativity, although we will see that there's some. But aspects as robotics or planning or social relationships are out of current technologies. But in general, the artificial intelligence tends to imitate the ability of animals to behave among them. And the central concept in artificial intelligence deployment is the neural network. Because artificial intelligence is artificial but inspired by the intelligence of living beings, those living beings often use neurons, a specialized kind of cells, to process information brought to them by another set of these kind of neurons, which are the sensory ones. So essentially, what a neuron does is take data from outside, accumulate it, because it takes it from many fellow neurons, accumulate this data, weighting it by several parameters, sum them, and if the sum is above a threshold, trigger a response and broadcast it. So this is the schematic of a neuron. So a neuron is a body where you have a multiply and accumulate part, and then an action potential that triggers the output. So if the input is this vector x with this other vector of weights, you multiply this with the dot product and sum, and then if this multiplication passes the test with the function g, then you trigger the output, okay? So typically, the g function, the activation function, was typically was believed to be sigmoidal like this, which means that if the accumulation of inputs is very small or much smaller than a threshold, there was no response, and only when this overcame a threshold, then there was a trigger. This is what people used to think, but soon they realized that much simpler functions like this operate much better. So this is the ReLU, rectifier function, which is most often used in artificial intelligence and machine learning techniques. I have to highlight that so far I'm focusing on how the behavior of biological neurons is mapped into software, okay? So you can think of these functions to be programmed in a computer so that you provide data as bits, and this runs through this kind of software. Now, these neurons are arranged into neural networks in which each neuron is connected to other neurons. Typically, there are feed-forward networks like this one, in which the neurons are arranged in layers, and each neuron is connected to many or all the neurons in the previous layer, so that this neuron here receives input from every neuron from the previous layer, and if the sum times these weights overcomes the threshold, then it triggers a response that it directs, for instance, this one, to all the neurons in the next layer. So as you can see, the signal that reaches the output layer here depends on not only the input data, but on all the weights that are in the middle, in the hidden layers, which is all those that are not the first or the last, okay? So this is a complicated mathematical process, but it can be mapped into data, is multiplied by the weights, producing this input to the action potential. If it triggers a response Y, which is fed into the second layer, which is fed into the third, and so on. And in the mission of the neural network is given input data, what should be the answer, the output layer? So this is what training has to deal with. So you have a training process in which you have input data and target output, and you have to find a function y such that for a given x, y produces the target output. And for this, you have to optimize all the weights, the w's in the middle of here. Okay, so you provide an x, and you have. So in order to find all the weights in the neural network, you have to do this many times and optimize this loss function, which is the output of a given data set, the distance between the target and the actual output. In order to optimize this, you have to find all the dependencies between the error function or the cost function and the weights in the middle and optimize them by backpropagation. So you use the chain rule in order to find the dependence on the error function to any of the weights in any of the layers, okay? And this is how it goes. Now, the neural networks can adopt many shapes, many different shapes, depending on their the function they are defined for. And this is only an example of many kinds of networks and how they organize. The shape of this is meaningful in the sense that depending on whether they have a waist in the middle, they can perform different functions, and they are optimized for those. But this is a very wide area. Now, I wanted to highlight the convolutional neural networks because this is the tool that is most often used for instance, image recognition. For instance, the way your telephone unlocks when you have your face in front of it is using a convolutional neural network. Essentially, what this does is scan a data with certain patterns like this. You have a set of data, which is this X, and you have different filters which represent different things. And you scan this through your data, and when you multiply these elements one by one, dot vector product here, accumulate and place it into this box here. If you move this one place here, the product goes there. If you move these two, and so on. So, for instance, this could be the scheme of operation of podometer, like the ones that you wear. How does it detect whether you have made a step? So imagine that a step is something like this. So if it detects this, you multiply this by this filter. This filter is step. Okay. So this X, is this a step? You multiply it and accumulate, and this gives 0 because when you integrate this dot product, this goes to 0. So this won't be a step. If you multiply this by this, you get this. You integrate this, and this is above 0. So this gives a yes. If you multiply this by this, for instance, you have this, and the accumulated is 0. This is not a step. So whenever you find this data for this function, you get a step only in this case. Okay. So this would put a 1 in a position. Obviously, this is a trivial example, but if instead of a series of data like this, you have a binary image, for instance, you run kernels like this, and you can detect a mouse, or you can detect, I don't know, parts of an end. You have one of these filters is a nose. You run this through here, and you place a nose somewhere. You have another one, which is an eye and a lip or whatever, so that at the end it can decide whether this image is a cat or a dog or a donut. Okay. Another special neural network is recurrent neural networks, in which there are no such thing as layers. The neurons are connected very arbitrarily among them, and even they can be connected to themselves. And this is most likely what the brain is like, although we'll come to another detail later on. The good news about this recurrent neural network is when they are used as reservoirs, because in this case, typically you have to optimize all the weights, both for the input, the output, and the relationship between the neurons inside. But you can make a different way of processing in which you only optimize the outputs. And this saves a lot of effort, a lot of energy, and a lot of time, and it is very efficient. And this is what reservoir computing is about. Because neurons are connected forward and backward and with themselves, this makes the system dynamic, because the state of a neuron depends on its previous state and on the previous states of other neurons. So this has a dynamical behavior. And this is a very adequate protocol to deal with varying signals, like speech recognition, for instance. It is very complicated, but it is very efficient. Okay, and this is it's usually called the third generation of neural networks, because the first generation was the Macaulay-Compits, which was step constant activation functions. They operated in a Boolean type of response, because they only answered yes or no, or 1 or 0. The second generation was the artificial neural networks, of which I've been speaking extensively now, in which the activation function was static, but they had a continuous response, because the action function was a function that varied, so it could respond strongly or weakly, and it was continuous. Actual neurons are believed to operate in a rather different manner, in the sense that they work by spiking. So when a neuron receives an input and it responds, it does by producing a peak of voltage between the inside and the outside of the membrane. And this pulse travels along the neuron by exchanging potassium and sodium ions. I won't delve into this, because my knowledge is very scarce. But essentially, the message that I want to pick for us now is that to a peak of input, the neuron responds if the impulse, the synaptic impulse, reaches a threshold, then the neuron responds with a peak, and then a refractory period in which it rests, and it's incapable of responding again. So it's like an excitable system, which is a concept now used with many processing systems, in which the response of the system makes it irresponsive for a while. And this is how these spiking neurons operate. So these spiking neurons usually work as leaky integrate and fire. So for instance, if a train of pulses come to a neuron and another train here, they are weighted by this weight here, weight 1 and 2. This is less than 1, and this is more larger than 1. When you sum them, eventually you can this sum to that. If you this is actually not invented. I put it exactly on in synchrony, and so the yellow line represents the sum of these two things, and the decays is the leaking of the potential. So if in this case it doesn't reach the threshold, so it decays, but this one pushes it up, and this one again, and this one pushes it a lot up, and this one even further, so it reaches the threshold, so it fires. And for a while, it cannot respond anymore. So the next one starts another pulse. And so from these two data coming through neurons, only these two outputs go outside through the axon, okay? This can be implemented with photonics or electronics or many other things, and they operate very, very nicely. So as you can see, my progress bar is very slow, so I think I have to accelerate a bit. Hardware for artificial intelligence. Essentially, most of the artificial intelligence is operated in computers. So it's not proper artificial intelligence, it's simulated, let's say. So essentially, there are electronic approaches in memory computing which try to avoid the von Neumann bottleneck and photonics, which I'm very fond of. But so I'm not going to talk much about electronics. Electronics is a very well-developed technology, and computer-oriented devices are in the form of CPUs, accelerator, graphic process units, which are very successful, and they are changing the economy of the world, FPGAs, ASIC, and so on. And those which are neuroscience-oriented are similar in implementation, but they have different inspiration, because they try to emulate electronic, with electronic, imitate the operation of biology devices like neurons. Now, as I said, von Neumann invented the computers as we know them today, and his architecture, if one could open a CPU, it contains a processing area and a data area, and data has to travel to the processing area and return. And this is done through the so-called the data bus. And because this bus is for going and returning, and the data resides elsewhere from the processing, there's a bottleneck that the operation cannot be faster, because the processor has to go and fetch the data, process it, and return it to the data area. And this is what is called the von Neumann bottleneck. So people wanted to avoid this and do something in which the computation and the storing was in the same place. And this is what some kind of devices like the memristive ones do. This is the most typical type of memristive device, which is a piece of oxide in which has two different contacts on different sides. One is a Schottky and the other one is an ohmic. And it so happens that if you measure the current versus voltage, you can drive it by applying a large voltage to one side and place it in a low or high conductivity state. And these conductivity states can be scanned by driving the voltage with low values. If you want to change from this low to this high slope curve, you have to go and polarize it strongly to one side or the other, and you can change its operation. So you can define two states of conductivity, which are like a bit, and you can change it, and you can use it both to store the energy and both to operate logics with it. So for instance, this circuit here is a so-called material implication, which has this truth table. 0, 0 is 1, 0, 1 is 1, 1, 0 is 0, and so on. And it was demonstrated by Whiteside and Russell that with this gate and the NOT and the OR, it was enough to make all the logics. So this circuit, which can be implemented with these two sort of diodes and these gates, can do any logic operation and can do any kind of computing. Now, this is a very promising material, a very promising device, because it can be made of, I didn't intend for you to be able to read this, only to be amazed by the amount of materials that can be used as memristors and the performances they have. So this, I know in this house there are people working in materials that are memristors, and the good news is that when they were invented, these materials were worn out very easily because they were thick oxides in which strings of defaults of defects were created while driving the current, and by doing this many times the material wear out, and it was problematic. But now if you grow them at nanometer scale, a few nanometers of material are sufficient to operate in this way, and they do not age with operation. Photonics is very appropriate technology for implementing artificial intelligence and has a long story. For instance, the upper half is the evolution, the highlights in the milestones in artificial intelligence, and the lower part is the milestones in optics artificial intelligence. As you can see, there's a delay, but many devices, many proposals have been made and realized with photonics. The big advantage of photonics is that it is massively parallel, can be done in free space, it's very energy inexpensive, virtually instantaneous. Think that, for instance, making a Fourier transform in a computer can take anything below between 1 microsecond and 1 millisecond. But if you place a lens at focal distance from an object, it creates the Fourier transform in no time. So, for instance, this is a way for image recognition. For instance, you have to detect the edges of figures of images, and with Fourier transform, you only need a lens and a pinhole, and you get the instant detection of edges. So this was a few of the characteristics of photonics in artificial intelligence, but it has, in addition, you can multiplex in time, in space, in polarization, in wavelength. So it's a powerful technique. I had a few examples, but I will only tell you that, for instance, this is a breakdown of the different approaches in photonics, and as you can see, even though you cannot read it, you can see that there are many that can be classified into stateless or stateful because they have a state like in reservoir computing, or they don't, but they can be implemented with numerous technologies. Like, for instance, in 1978, this was an example of multiplication of a vector times a matrix. Just by using a cylindrical lens, the diodes in this array are projected onto this matrix, which is an LSLM, which is a filter that can be switched on or off pixel by pixel. So if you place a cylindrical lens on the other side rotated with respect to this one, you project this multiplication on this row. So what you are doing is multiplying a vector times a matrix. This may seem trivial, but it is a fast, easy, and efficient method. Matrix multiplication, multiply and accumulate is the name of the game in computing these kind of things. And if you realize a beam splitter can do this very easily. If you send a beam of light of electromagnetic field X in this direction and this one on this direction, you get the sum in this port and the difference in this one. If you transform this into electricity, you can multiply them very easily. So this is also very fast and very convenient. This can be used either with this technique or by Mach-Zehnder interferometer to create integrated circuits that operate like electronic circuits, in the sense that you input the signal on one side, it goes through many turns and twists inside, and you have electric action over the Mach-Zehnder, because you can change the temperature on very small, on each of these Mach-Zehnder. So you can dephase one or the other. The multiplication depends on the phase, and so you get the answer on the output. I never tire of highlighting the virtues of reservoir computing, because, as I said, it is an approach in which you don't worry, you don't care about the actual weights in the many neurons that constitute the reservoir. You let them be what they are, and you only operate on the output. And for instance, if you use a multimode fiber, that it can contain many modes, optical modes, that can be considered neurons, and their interaction and exchange of electromagnetic field is what the weights represent. So you can input information coded with an SLM on one side, let them mix on the output, and you can train a camera to interpret this as so you only have to optimize the weights on the output, okay? This was an example in which you use a space sort of reservoir, but you can do also in time. For instance, if you have a loop, a fiber loop, in which you feed information, and if the information returns to the laser, for instance, if you have a laser connected to a loop, the light that the laser emits returns to the laser, and it changes its oscillation, and it can go into a very nonlinear regime. So if you send, if you modulate the input that you feed into this fiber, you create a reservoir in which the nodes, like in the fiber, the modes are not spread in space, but are spread in time. So if you have a counter that reads these modes as they pass in front of you, and then you optimize the multiplication table, you can make this compute as well. This is a very effective and simple means of using reservoir computing. Okay. This is how artificial intelligence can be done in the laboratory, and this is something that some of us are interested in. But now we enter into what can artificial intelligence do for those who are doing research into material science. The use of machine learning often adopts one of these three kinds of strategies. So you can use supervised learning, in which you train a system with data, and then you ask it to interpret new unknown data to it. And supervised learning, you feed the machine learning, you feed the neural network, and it trains itself, okay? And finally, I'm not going to talk about it, but reinforcement learning is like the way in which animals or babies learn, because if they hit a door and it aches, they don't do it anymore. And so they are reinforced by success or failure with prizes or punishments. But essentially, these three methods, the supervised machine learning approach, you feed a structure and a property, and you find the relationship between them. So this is good for image recognition, for instance. You have a machine learning system in which you provide thousands of pictures of dogs, and you say all the time, this is a dog, this is a dog, this is not a dog, this is a dog, this is not a dog, and the machine learns to identify dogs. And then you train it with cats or whatever, and at the end, when the machine is trained, you feed an unknown picture, and it decides whether it's a dog or a cat. Essentially, it depends on having data labeled. The unsupervised machine learning approach relies on a bottleneck layer. So the layers of neurons are big at the beginning and narrow down to a bottleneck. And the way these machines are trained is the machine learns to identify the essential features of the data, and then it regenerates it. And if what it generates is what it was fed with, then it keeps these weights. So essentially, in this case, the machine is capable to do this kind of clustering, dimensionality reduction, and classification of things. So because if you train a machine to identify cats, it probably is irrelevant if the background is white or gray or green or yellow. So the background is an irrelevant data part. So there's a dimension that is unimportant. And this is what this bottleneck layer is. For instance, you may train a machine to compute the transmittance of a double barrier potential. You give many double barrier potentials to the machine, and it learns that the essential data in those potential is the height of the barriers and the width of the barriers. So at the end, it will discard all the data except these two. So you can realize that you can narrow the bottleneck to the essential dimension of the problem. Okay. I have the reinforcement operation trains the agents, because it's agent-based, to respond to the outside conditions and to deal with the environment. Okay. There's a special case of these examples in which is called the generative adversarial networks, in which two machine learnings operate against each other. It's like a policeman and a thief. So one tries to deceive the other, and which is the generator, and the discriminator has to decide whether the data generated was false or true. And when this operation has a success rate of 50%, they are properly trained, and you can use the generator to create data which is useful. Okay. So in the training process, they mutually feed each other. The generator gains from tips provided by the discriminator, and the discriminator gains from real data. So this is a typical approach for optimizing materials, devices, and structures. Okay, because I'm not a software person, I'm not much concerned with the actual software with which you can run these machines, but if you go through Google, you can find find many, many resources in which you have algorithms, libraries and data and so on. And we are approaching the real applications. I'm going to hover over a few examples. I've tried to divide them into different classes, like discovering new materials, simulating materials, predicting properties, and characterizing materials. And for this, I have to stop a bit and examine a few examples. So the active learning, for instance, uses models like ab initio computing, calculations, or feeding from available data already, and propose new candidates based on this kind of properties. The generative design builds, like I said earlier, a latent space in which you can choose then, you have a broad machine, a broad neural network with a bottleneck, and the dimension of this bottleneck is a space where you can find many candidates that with the decoder can be converted into actual data, which are candidates for the property that you're looking for. Data mining is data analysis and search strategy in which you examine available data in the form of text, for instance, and you discover things that only statistics can reveal, but are very hard to find by reading by a human. Text mining is something similar, and it only feeds from actual written data. It's very convenient because there are many things that can only be conclusions that can be drawn from the observations of many that never realize each on its own how important it was. For instance, this is a text mining example in which the machine is provided with more than 3 million abstracts from papers published up to 2017, I think it was, 19. The data was one hot coded into, I think it's 200 dimensions, and then it was fed to the neural network, and it was compared by vector proximity. So essentially what it checked was the angle between these vectors. So you could compare the nearness of these concepts. For instance, these are materials, and this is the histogram of the properties. They are near in the text too. So for instance, these two materials are near cathodes and electrochemical, and they are thin and so on. And using this and feeding the data, this is the year that you run the experiment. So you have your corpus of data, which is the literature from 1800 to 2002, for instance. If you feed the data to 2002, you can predict the existence of this many percent of available actual real materials. So for instance, the more data you feed, the more percentage of actual later discovered materials you have. Obviously, the more data you feed, the more percentage you reach. So this was published in 2019. If you cut the data much earlier, you find less, you can predict less later discovered materials, okay? High throughput design is a machine learning in the sense that it relies on data handling using database, the building databases, and then mining them to discover new materials. And this is an example in which they tried to discover new intermetallic compounds made of this series of elements. And the upper half of the matrix represents how likely it is that they mix. These are not mixing, these are mixing. And the lower triangle represents how many hits the prediction achieved, because this is predicted. This represents a pair of materials, of elements that mixed, and the experiment also found that they mixed. And as you can see, most of the triangle are either green or gray, because these are the ones that do not mix, neither in the prediction nor in the experiment. So most of this triangle is a hit, whereas there are some, these red ones and these blue ones are misses. Another example in property prediction is this finding structure-property relationships, and in this case you chart the landscape by these coordinates like composition, structure, morphology, and so on, and associate that to the property, and with that you can create a machine that learns by experience, like for instance to prepare an automated autonomous loop of materials fabrication and optimization. So it starts with an arbitrary mixture, for instance, of these precursors. It mixes them, it casts them into a thin film, it anneals them, then it scans the image of it, records the optical spectra and the electrical properties, calculates how far from the objective it is and what the next step has to be in order to improve it. And this, as you can see, this is 13 minutes, 7 minutes, 1 minute, and every cycle takes less than 20 minutes or thereabout. And in this way, the machine alone can optimize a material for a property that is sought after. Obviously, characterization, I'm not going to enter into any details of this, because characterizing in the aiding, like for instance, the image techniques, diagnosing X-ray diffraction patterns, or neutron or electron and so on, phase determination, X-ray again into play. This is similar to image recognition, because you can train a machine to understand that this pattern corresponds to this material, and then you give a new pattern and it knows which material, if it was properly trained, obviously. And not only materials, but things that you can do with materials can also be optimized using these machines for instance, inverse design. If you have a performance, a property that you want to optimize, what you want is to compute the gradient of this performance function and equate it to 0, in which case you know that it is maximum or minimum. And that has to be within the constraints imposed as physics. So G is X, the data of the structure and the parameters are related by a function. So you run this machine and it gives you an answer in which you have a device, for instance, in this case, that gives a maximum transmittance and minimum transmittance on different ports as a function of wavelength, for instance. One of the advantages of this is that it is very effective, but it doesn't tell you why. So this is one of the things that artificial intelligence has. It's a black box, and you don't understand why things happen. For instance, this is an example in which they wanted to optimize the structure of quantum dots by measuring their properties, the optical properties. This is transmittance or reflectance or absorptance or whatever. So you have a neural network in which you have 3 inputs, which are the radii of the 3 shells that compose this kind of structure. you run it into the machine, and the output is the spectrum, which is provided by the output neurons. And you have to optimize this by training it. You compute this structure many times exactly because you can, and then you ask for a spectrum, and it gives you the material that fulfills this property. This is a generative adversarial network in which you train it with these yellow patterns, and then you provide a spectrum, and the generator creates a pattern. This is one sense of the G, and the pattern goes through a simulator that can solve the electromagnetic equations and provides a spectrum. So if the spectra in the input and the spectrum in the output are the same, then the two machines are working properly, because you give it a pattern and goes through. You give it a spectrum, goes through a pattern, and returns to the spectrum. So the generator and the simulator are operating properly. Now you give a new pattern, and the discriminator has to say whether it is true or false. And in this sense, then this is an example of operation. The yellow pattern goes through the simulator and produces a spectrum, and this spectrum is fed into the generator. This is the initial pattern, and the generator ends up producing a black pattern. And if you compute the properties of this black pattern through an ordinary finite element method, it produces this spectrum. Okay, so if you compare this spectra and this spectra, they are virtually the same, and that means that when you create a pattern, you can retrieve the actual the generative adversarial network retrieves the actual parameters very properly. So, for instance, this is an example in which you ask it to produce this kind of spectra, and the machine gives this response, which has this spectra, which is acceptably similar to the what you asked. So here we are at the end. My conclusions are very arguable. Artificial intelligence is artificial. So you have to be content with what you have, because it is not human yet, and hopefully for a while. It needs you steering it, because it's not spontaneous, and it needs input and its direction until it reaches the state in which the general artificial intelligence is achieved. It is very powerful, but it's very power hungry. For instance, training one of these large language models, of which many of our new cell phones benefit, produces a carbon footprint similar or equal to that of a car in its whole life, from production to the scrapyard. And there's a lot to be done, like new computing strategies. There's huge amount of imagination have been invested in this, and also there are many materials that we do every day and we are capable of doing, which can be applied into new ways of computing. So this is good news for us and good news for all. And this is the end.
So thank you very much, Cefe. I mean, this is a huge topic to summarize in 1 hour. You did a wonderful job of it. Now, any questions, comments? If not, maybe I can kickstart the discussion with... there was a question?
Thank you very much. You gave this example of this quantum dot. This was supervised learning, I guess?
Yes.
And can you also kind of extend it to unsupervised learning? I mean, can you kind of give us ideas what to do next?
Well, as I said, supervised learning can give you inverse design, for instance, optimization and so on, but unsupervised learning can only is capable of classifying things or finding dimensionality reduction and so on. So if you want to make a quantum dot that emits here or there and so on, you cannot use an unsupervised learning machine because it only tells you whether this quantum dot emits in green or yellow or blue or things like this. It's for classification.
Yeah, thank you for the very interesting talk. I have a quick question about when you were talking about how to do calculation with photonic devices, when you showed the example of the Mach-Zehnder interferometers. This is very big compared to the electronic transistor technology that we are using right now. Do you think there's like opportunities to make photonic computation a lot smaller, or maybe like to scale it even in 3D?
I don't know if I'm not biased, but nobody tells exactly what you said. Optics is wavelength, micron wavelength, so devices, gates are going to be micron wavelengths. So you nowadays electronics is in the 5 nanometer step, which means that things are about 5 nanometers, the minimum feature size. The minimum feature size with photonics is going to be micron. So the footprint of the processor is going to be huge in comparison. This is good news and this is bad news. For me, it's good news because I don't care about this circuit implementation. I'm a believer in reservoir computing in which you don't care about what you have. There's an example of reservoir computing performed with a bucket of water. You have a bucket of water, you have piezo electric cells and microphones on the other side. You excite ripples on the water and read them with the microphones, and you can compute with that. You don't care what happens, if it is water or if it is alcohol or if it is oil or whatever. So you only care about optimizing the readings and coding properly the input.
Thank you.
So, any more questions or comments? I have to say, I don't really understand what this reservoir computing is about. Can you perhaps show us?
I can, certainly. You will understand what reservoir computing is in comparison with ordinary feed-forward neural networks. So in an ordinary neural network, you have this feed-forward. So this neuron is going to send its output to all the neurons in the next layer. So to this neuron, signal comes from here, from there, from everyone. It sums and multiplies, accumulates and accumulates, and then it broadcasts to the next. In a reservoir computer, any neuron can be connected to any other. So this one can send to this, and this to that, and this to the last, and this to itself.
So the connections are
So the connections are recurrent. They are called recurrent neural networks. So in this case, you have neurons that are connected, this one, to itself, and to this one. So this is the way. So computing the backpropagation procedure here is virtually impossible. It's very difficult because it's impossible to systematize how you derive the variation of the cost function with respect to the weights. So in this case, the approach is you input your information here and you read the output there. But instead of computing all these things here, you forget about it and you only optimize this here. So the cost function is going to depend only on these weights here. So you have to be ingenious.
Why do you need the rest of the
This
network
is,
then?
this is a very good question which I'm not prepared to answer.
Okay.
Nor is many people, nor are many people. The fact is that this operates wonderfully, and just as nobody understands or care why machine learning sometimes gives some answers, like for instance, in the game of Go, there was a match that was lost by the machine, and actually this young Korean guy won, and everybody was surprised or preoccupied because the machine went crazy and something went amiss. In this same manner, the operation of what happens inside is unimportant, and you can have enough with optimizing these weights here.
Okay,
This is incredible, and this reservoir computing and extreme learning derives from here. It's a lot more economic, a lot more efficient, and it works.
I clearly have to get my mind around this. Sounds very interesting. Well, any more quick questions or comments? If not, let's thank Cefe again for a very interesting talk.